Welcome to a presentation on GoogleNet, the winner of the ImageNet Large-Scale Visual Recognition Challenge in the year 2014. GoogleNet introduces new techniques and insights for image classification, and that's the subject of this presentation. GoogleNet is the first network to come along in 2014 that's geared towards efficiency, and by that we mean smaller and faster models. Prior to GoogleNet, we've seen convolutional neural networks such as AlexNet and OxfordNet introduce successful tools such as pooling and dropouts for regularization. Reasons we should care about GoogleNet are that GoogleNet consumes 12 times lesser parameters than AlexNet. At the same time, GoogleNet is significantly more accurate than AlexNet. Lower memory use and lower power use are paramount for mobile devices. GoogleNet stays within the targeted 1.5 billion multiply ad budget at inference time. Overall computational cost is less than twice compared to AlexNet, although the network is much bigger than AlexNet. At the heart of GoogleNet is the Inception Module, and this presentation introduces the Inception Module, the microarchitecture on which the Google macro architecture is built. The evolution in convolutional neural networks had its start in 1989 in a modest network with three hidden layers. It consisted of a layered network composed only of convolutional and subsampling operations, followed by fully connected layers and ultimately a classifier layer for classifying handwritten digits. The connections for the lower two layers in the network were convolutional, and the connections for the upper two layers were fully connected. Each hidden layer is a higher level representation of its lower layer. It's worth studying this simple architecture since most modern networks have a similar architecture, albeit more recently we've seen newer layers such as pooling and dropouts that help with overfitted models by reducing the number of parameters. The input is a 16 by 16 image with a single grayscale channel. The output layer produces a code which is one of the 10 handwritten digits that were presented at the input. Let's look at the first hidden layer H1 and its connections to the input. The hidden layer H1 has 12 feature maps, H1.1 through H1.12. The kernel size is 5 by 5 and the stride is 2. That means the input image is undersampled by half. Thus, each feature map is of size 8 by 8, giving us a total of 12 times 8 times 8, 768 hidden units for H1. Let's compute the total number of connections. This equals the number of hidden units H1, which is 768, times the number of channels, in this case one grayscale channel, times the kernel size, which is 25, plus a bias term for each of the 768 hidden units. Let's also compute the total number of parameters. Since this is a convolutional layer and we share the weights applied to each image batch, the total number of parameters is the channel size times the kernel size times the number of feature maps, in this case 12, plus the 768 bias terms for each of the hidden units. Now let's look at the connections between the hidden layers H2 and the hidden layer H1. H2 also has 12 feature maps, H2.1 through H2.12, but the connections between H1 and H2 are heavily constrained. Each of the units in H2 combines local information coming from only 8 of the 12 different feature maps in H1. This was done for an important reason, that is, to break the symmetry in the network and thus improve learning. The convolutional kernel size is 5 by 5 and the stride is 2, and that gives us 12 times 4 times 4, 192 hidden units. The total number of connections is calculated as follows, and that is the 192 hidden units times the size of the kernel, 25, times the 8 channels coming in from the H1 layer, plus the 192 bias terms. The total number of parameters is likewise constrained to the kernel size of 25 times the 8 input channel times the 12 feature maps plus the 192 bias terms. Now we look at the connections between hidden layer H3 and hidden layer H2. The layer H3 has 30 hidden units and it is fully connected to H2. Finally, the output layer has 10 observable units and it is fully connected to H3 as well. Fast forward to 2012, and it was a watershed year where the top 5 error in the ImageNet contest dropped by more than 9% because of the use of a convolutional neural network, now referred to as AlexNet. Since the resurgence of CNNs in 2012, variants of deeper and deeper CNNs have won the ImageNet contest. And by contest we mean the annual ImageNet large-scale visual recognition challenge. The graph shows that deeper nets with more parameters to learn do better at classification. The extreme case being ResNet, the winner in 2015 with 152 layers, while GoogLeNet, the winner in 2014, used a relatively modest 22 layers. Later, we'll look at the idea put forth by GoogLeNet called Network in Network, which is a micro network embedded within a macro network. Before we do that, let us review the architecture of a conventional neural network up to this point. A typical design pattern for convolutional neural networks, or CNNs, is as follows. We have a stack of convolutional layers with kernel sizes as high as 7 by 7 and 11 by 11 and strides such as 1 or 2. Interspersed between convolutional layers are contrast normalization and max pooling layers. The penultimate layers towards the end of the network were typically fully connected layers, although that's no longer the case with the introduction of global pooling layers. The last layer is typically a loss layer, which encapsulates a loss function. And that hasn't changed. Dropout layers were introduced to reduce the number of connections and overcome problems of overfitting. With this type of approach, the trend has been to increase the number of layers to get higher accuracies. Here we highlight the computational and economic challenges of very deep neural nets. Mainly there are two challenges. Number one, adding layers increases the number of parameters and makes the network prone to overfitting. As we are in the supervised learning domain, the larger networks need more data, and even with data augmentation techniques, the amount of data may not be sufficient. Of course, gathering and annotating more data will be expensive. Second, Deeper networks lead to a computational explosion. Linear increase in filters results in a quadratic increase in compute. Also, if weights are close to zero, we wasted compute resources. Fast forwarding from 2012, which marked the birth of AlexNet, to 2014, when the designers of GoogleNet took aim at efficiency and practicality rather than a sheer fixation with accuracy. Overall, a good thing. The resultant benefits of the new architecture were that the model size was 12 times less than AlexNet and significantly more accurate than AlexNet. Lower memory use and power use are vital for mobile devices, as we're well aware. Also, the designers had a compute budget of 1.5 billion multiply add operations, and they met that goal as well. The computational cost was less than 2 times compared to AlexNet, which is an 8-layer network, whereas the GoogleNet is a 22-layer network. The inspiration guiding the Inception module is earlier research work that theoretically proves that optimal neural nets can be built if we cluster neurons according to the correlation statistics in the dataset. These findings can be applied layer by layer, that is, we analyze the correlation statistics in the previous layer of activations and cluster neurons with highly correlated outputs for the next layer. These findings are immediately relevant to images where there already exists high correlation between local pixels in a neighborhood patch. So we can cover them by a small one-by-one convolution. Additionally, correlation between a smaller number of spatially spread out clusters can be covered by 3x3 and 5x5 convolutions. These findings also suggest that we can apply all the convolutions on the patch, the 1x1s, the 3x3, and the 5x5, instead of picking one of them. The theory also suggests that we could apply a max pooling layer in parallel, and that's what is done, as we see later. This slide visually summarizes what we said earlier. 1. In images, correlation tends to be local, so we can cluster the neurons simply by taking convolutions on local patches. And 2, we can cover local clusters by small one-by-one convolutions. We can cover more spread out clusters with 3x3 convolutions, and we can cover even more spread out clusters with 5x5 convolutions. And then we want the effect of all of them, so we stack or concatenate them on the same patch. So conceptually, the Inception module is simply the concatenation across 3 convolutional scales: a 1x1 convolution, a 3x3 convolution, a 5x5 convolution, and a 3x3 max pooling. One of the intuitive and practical benefits of using multiple width convolutions on a single patch is that visual information is being processed at several scales and then aggregated for the next stage. This improves the discriminatory power of the network, but there is a big problem. The network as conceived increases computation several fold when we have a large number of feature maps. This slide shows the solution to the computational explosion, which is the idea of dimensionality reduction. One-by-one convolutions are used to reduce the dimensions before the expensive 5x5 convolutions and 3x3 convolutions are used. Each of the blocks shown here also includes a rectified linear unit activation or ReLU, making them dual purpose. Now that the compute budget is controlled, this allows the network to have more stages. We should note that the Inception module gives us the knobs and levers for a controlled balancing of compute resources and speed, resulting in networks that can be 3 to 10 times faster. Therein lies the value of the Inception. We now succinctly summarize the insights presented so far. GoogleNet analysis leads to the following architecture choices, which is insight number one. So choosing filter sizes of 1 by 1, 3 by 3, and 5 by 5, and no higher. Applying all three filters on the same patch of image, no need to choose any single one of these. Concatenating all filters as a single output vector for the next stage. Concatenating an additional max pooling path, since max pooling is essential to the success of CNNs. Google insight number two. Decrease dimensions whenever computation requirements increase via a 1 by 1 dimension reduction layer. Use inexpensive 1 by 1 convolutions to compute reductions before the expensive 3 by 3 and 5 by 5 convolutions. 1 by 1 convolutions include a 1 by 1 ReLU activation, making them dual purpose. We're now ready to talk about the prior groundbreaking research in the network-in-network concept that was yet another source of inspiration for the GoogleNet designers. Think of the Inception module as an independent microarchitecture being replicated at each macro layer to create the GoogleNet macro architecture. To create a deep network, we just need to stack Inception modules side by side. Between these Inception modules, occasionally insert max pooling layers with stride 2. The stride of 2 decimates by half the resolution of the input grid. Experimentally, the designers found that stacking Inception layers benefits the results when used at higher layers. Lower layers are kept in traditional convolutional fashion. Stacking allows you to tweak each module independently without uncontrolled blow-up in computational complexity later, and therein lies its benefit. This visual shows the stacking of the Inception modules within the GoogleNet macro architecture. We introduce a average pooling layer and a linear embedding layer, which I'll explain in the coming slides. Because the network is rather deep, the designers of GoogleNet were concerned about the gradients vanishing in the intermediate layers during backpropagation of errors. This could possibly happen due to dead ReLUs, in which case the weight updates cease to occur and the hidden units stop learning. To combat this phenomenon, the designers used the intuition that the intermediate layers do have discriminatory powers since they already have higher representations of the image. So, why not tap into these intermediate representations and use them for the backpropagation of errors? To do this, they append auxiliary classifiers to the intermediate layers. During training, the intermediate losses were added to the total loss with a discounted factor of 0.3. The details of the network are shown in the next slide. The last insight that GoogleNet provides is the idea of replacing the fully connected layer at the end of the network with a global average pooling layer. Fully connected layers are prone to overfitting which hampers generalization. Luckily, global average pooling has no parameters to be learned and thus no overfitting. The overall network benefits from lesser parameters as well. We see that same principle used in yet another network called SqueezeNet, which also utilizes the concept of network-in-network. Note that global average pooling does not exclude the use of dropouts, a proven regularization method to avoid overfitting. Note also that GoogLeNet provides a linear layer at the end of the network for adapting the network to other labels. This is helpful when you are working on your own problem that needs to classify just a few classes. This concludes all the insights provided by GoogLeNet. Now we quickly summarize all the 5 insights that we've discussed so far. Number 1, exploit fully the fact that in images correlation tends to be local. Concatenate 1 by 1, 3 by 3, and 5 by 5 convolutions along with max pooling for every image patch. Decrease dimensions whenever computation requirements increase via the 1 by 1 dimension reduction layer. Number 3, stack inception modules upon each other from the principles of network-in-network. Number 4, counterbalance backpropagation downsides in deep networks. Use intermediate loss layers in the final loss. End with global average pooling layer instead of a fully connected layer. And that concludes this presentation.